Welcome back to the course of chemical crystallography. In the previous lecture, we have learnt about the Friedl's law can be derived from the expression of structure factor using vector space diagram. So from here we would like to continue and we would like to now derive the expression for structure factor with electron density. This is what is our motto for today's lecture. So what we want to do is we want to derive an expression which will relate FHKL in terms of rho xyz, which means we want to establish the relationship between the structure factor with the atoms that are present at various positions in the unit cell. Here we know the electron density rho is nothing but number of electrons present per unit volume. So suppose we have an atom located at xyz. We have an atom at xyz. So the electron density associated with that atom can be written as rho xyz, and if the volume element involved to accommodate that atom at xyz is dV, so the electron density associated with that atom is rho xyz dV. So in exponential form, this density can be written as rho xyz e to the power 2 pi I hx plus ky plus Lz dV. So now we have a large number of such atoms located at various sites in the unit cell. So when we want to add the contribution of all such atoms and then relate it to the corresponding structure factor, then for scattering from all those electron density sites, that is all the sites located at various xyz, so having the volume element dV, we can write the expression for structure factor as FHKL equal to sum over V rho xyz e to the power 2 pi I hx plus ky plus Lz dV. Let us write this equation as equation number 1. We will need to refer to this equation in future in the next part of this lecture. So let us try to now understand what is 1D. Let us now try to understand what is one-dimensional Fourier series, because we will need these mathematical tools to understand the relationship between structure factor and electron density. So a one-dimensional Fourier series can be written as fx equal to a0 plus a1 cos 2 pi x plus a2 cos 2 pi 2x plus the sign terms. So this should go up to an cos 2 pi nx and then we add the corresponding sine terms, which are b1 sine 2 pi x plus b2 sine 2 pi 2x plus up to bn sine 2 pi nx. It is in one dimension. So, in a simplified manner, one can write it as a0 plus sum over n equal to 1 to n an cos 2 pi nx plus bn sin 2 pi nx. So, we write this equation as equation number 2. So, now we know that cos x is equal to half e to the power ix plus e to the power minus ix, and sin x equal to minus I by 2 e to the power ix minus e to the power minus ix. So, now if we try to rewrite the expression for fx in terms of sine and cos terms, because it is already written in cos and sine terms, and when we will represent them using these exponential factors. So, fx will become equal to a0 plus half is taken out, it is equal to a1 e to the power 2 pi I x plus a1 e to the power minus 2 pi I x plus a2 e to the power 2 pi I 2x plus a2 e to the power 2 pi I minus 2x, minus 2 pi I e to the power 2 pi I 2x, and so on. These corresponds to the a terms, plus the b terms, which will have the minus I by 2 b1 e to the power 2 pi I x plus b1 minus b1 e to the power minus 2 pi I x plus b2 e to the power 2 pi I 2x minus b2 e to the power 2 minus e to the power minus 2 pi I 2x, and so on up to the n. So, when we try to do the sum of these, we can see that there are common factors which can be taken out and rewritten. So, what we try to take out is the terms with e to the power 2ix at one place, e to the power minus 2ix at another place, and so on. So, in the next page we will rewrite this expression for fx. We will rewrite this expression for fx equal to a0 plus half a1 minus b1 a1 minus I b1 e to the power 2 pi I x plus a2 minus I b2 e to the power 2 pi I 2x plus so on plus half a1 plus ib1 e to the power minus 2 pi ix plus a2 plus ib2 e to the power minus 2 pi I 2x and so on up to the nth term. So, this expression can further be simplified as a0 plus this expression can be further simplified as h equal to minus n to plus n ch e to the power 2 pi I hx we write it as expression number 3 where C0 is equal to A0 and CH is equal to half AH minus IBH and C minus H equal to half AH plus IBH. So, one can write the same as Fx equal to sum over H equal to minus n to plus n Ch cos 2 pi Hx plus I sin 2 pi Hx. So, this is the expression for a one-dimensional Fourier series along x-axis, say. So, what we know is that the electron density, which is rho xyz, is a three-dimensional periodic function for crystals. So, the overall rho xyz can be represented as a sum of this Fourier series in 3 dimensions with h prime, k prime, sum over l prime, c h prime, k prime, l prime e to the power 2 pi I h prime x plus k prime y plus l prime z. So, this is the expression number 5. These values of h prime, k prime and l prime can be from anything from minus infinity to plus infinity, because there are infinite number of planes that one can consider within an unit cell. So, what one can write in that case for f hkl is nothing but sum over v triple sum over h prime, k prime and l prime, ch prime, k prime, l prime e to the power 2 pi I h prime x plus k prime y plus L prime z into e to the power 2 pi I hx plus ky plus Lz dV, which is my equation number. No, we don't write any number for this. This equation comes from the equation number 1, because if you see the equation number 1, we have rho xyz. This rho xyz is now represented in expression number 5, and now rho xyz is placed in case of equation number 1, and we can write FHKL equal to the triple sum over h prime k prime L prime ch prime k prime L prime e to the power 2 pi I h prime x k prime y L prime z and so on. So we can write this as sum over v h prime sum over k prime sum over L prime c h prime k prime L prime e to the power 2 pi I h plus h prime x plus k prime y plus L prime z dV. So if this is a periodic function, so the exponential function is a periodic function here, and what happens is when we do the integration over a period, then it is 0 for all the terms. The integral over a period of an exponential function is 0 for all the terms except for the terms where h prime equal to minus h, k prime equal to minus k, and L prime equal to minus L. So what happens when we arrive at those two situations? In a situation when it is h prime equal to minus h, k prime equal to minus k, and L prime equal to minus L, we can write f h k L is equal to sum over v c h bar k bar L bar dV, which is equal to v into c h bar k bar L bar. So this is the expression number 6. So one can write the constant c h prime k h bar k bar L bar as equal to 1 by v f h k L. We write it as equation number 7. So now we substitute this equation number 7 to equation number 5. What is equation number 5? The equation number now we substitute this value for c h bar k bar L bar to the equation number 5 and rewrite the expression for rho. So what is rho xyz? It is equal to 1 by v triple sum over h K and L, FHKL e to the power minus 2 pi I Hx plus Ky plus Lz, which is the equation number 8. So now if you try to compare this equation number 8 with the equation number 1 that we wrote, so I am again rewriting that FHKL is equal to sum over V rho xyz e to the power 2 pi I Hx plus Ky plus Lz dV. So this was my equation number 1. What do we see here in these two very important expressions? In case of equation number 1, we are expressing structure factor as a Fourier transformation of rho xyz. So here the structure factor is expressed as a three-dimensional Fourier transformation of rho xyz, which is a periodic function in 3 dimension. But in the equation 8, we see the reverse. Here the rho is expressed in terms of FHK. What does it mean? Here the density, that is the electron density, is expressed as a Fourier transformation of structure factor FHK. So what does it mean? If we have a set of structure factors, if we do a Fourier transform of structure factor, we get to know the electron density at various places. And if we do the reverse, we take the electron density and do a Fourier transformation, we get to know the structure factors. So this Fourier transform and inverse Fourier transforms is done every now and then when we try to refine and compare the structure and the modified structure along with the model, which we will discuss in future. So in this lecture we have learned till now how one can express the structure factor FHKL in terms of rho HKL and how one can represent rho HKL in terms of FHKL. So now let us extend our understanding of structure factor using the exponential form. So today now we would like to learn the structure factor expression in exponential form. So once again, for our use, we need to know a few mathematical expressions. We need to know the expressions for e to the power x, which is 1 plus x plus x square by 2 factorial plus x cube by 3 factorial plus x to the power 4 by 4 factorial and so on is now the equation number 1. We write cos x equal to 1 minus x square by 2 factorial plus x cube x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial and so on. We write it as expression number 2. And then we write sin x equal to x minus x cube by 3 factorial plus x to the power 4 by 4 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial and so on as equation number 3. Now if we substitute x by I delta and multiply both sides of equation 1 by f, we can write f e to the power I delta is equal to f into 1 plus I delta minus delta square by 2 factorial minus I delta cube by 3 factorial plus delta to the power 4 factorial and so on. So one can write this f e to the power I delta equal to f 1 minus delta square by 2 factorial plus delta to the power 4 factorial minus and so on plus take I out delta minus delta cube by 3 factorial plus delta to the power 5 by 5 factorial and so on. So this can now be written as f cos delta plus I sin delta. So now this is nothing but a complex number in polar form. So this complex number has an amplitude of f and phase angle delta. So we can write the structure factor f is equal to sum over j fj e to the power I delta j, where fj is the scattering factor of jth element and delta j is equal to the phase of the atom with scattering factor Fj with respect to the origin. So, this is the phase of that diffracted beam because of that Fj. So, now we can write f the structure factor Fhkl as equal to sum over j Fj e to the power 2 pi I Hxj plus Kyj plus Lzj, as the phase delta is nothing but 2 pi Hx plus Ky plus Lz, and here since we are doing the sum over all possible x, y and z, the subscript j's have come in. So, this is the expression for structure factor which we have already seen in our previous lectures, how this is represented in terms of the exponential form. So, in today's lecture we have learned how to represent the structure factor using the exponential form, using the polar form and so on, and then we have learned how to correlate the structure factor with the electron density. So, what we now know is the structure factor is the Fourier transform of electron density, and electron density is a Fourier transform of structure factor. So, in the next class we will learn about special structure factor expressions, and then we will try to derive the systematic absence conditions.